Hello, Jason here from Instruō. In this video I'm going to be focusing in on a couple of design stages that are pretty typical in my process of developing a module. The whole project is kind of centered around the ceithir, which is this very large 58 HP quad multimode filter. I've been documenting the whole process kind of behind the scenes as I've developed this. The module itself, it's getting pretty close. This is currently version 1.0, but there's a 1.1 build in the rack upstairs that's being tested with. So we're entering pre-production, but this video is going to be stepping back a bit and looking at the first prototype iteration of this module, which took the form of a module. So it's actually a quarter of it. I focused in on just quartering the layout and testing a single iteration of the circuit, of the filter, because there are quite a few changes to the schematic versus previous filter designs that I've done that are in the same multi-mode style. Yeah, so the video itself, it's going to be a bit of commentary that I'm going to record today, looking back over some time-lapse recording of the schematic capture process and then board layout. Things were done a little bit differently for this because I knew this was not going to be the final hardware format, because it's only a quarter of the module, or less than a quarter of the module. I didn't need to worry too much about efficiency of the layout. I was focusing in on getting the circuit placed and built so that I could confirm it worked, essentially. But I knew there would be mistakes, so the main part of this video is me upstairs at my soldering station with I rigged up a sort of multi-camera setup and had a top-down microscope and stuff, and it's me working through this exact hardware build. So this is the only one that came to fruition from this board layout, but it let me confirm what was broken and figure out how to fix it. So you can see there are Trimpots hot glued onto the back of this. There's a lot of fine gauge jumper wire. There are circuit bends all over this hardware. Yeah, it's a little bit messy. So the video that I captured upstairs is kind of it actually served its purpose as a note to self. This was me documenting the changes that I'd made so that I could then update them in the final schematic for the next iteration. So this is the layout as it came about. It's 2 PCBs, which is bigger than it needs to actually be for one of these filters, because if we look at the later stage, it's 4 of these filters plus the mix and modulation stage, and I simplified it down so that the filter core boards are their own sub-modules, but all the circuitry per filter is kind of contained to a single board. So this ended up being a little bit more spread out than it needed to be, but that made it easier to circuit bend and make changes. If anything, I could have made it bigger and given myself less microscope necessity, but it worked, and it's quite a satisfying part of the project, I think. It's a very different stage from the schematic drawing and then tracing. It's very physical, very practical. So hope you enjoy. This video covers a few different stages, but hopefully gives a bit of a glimpse into my process of designing a module and how that maybe relates to other design approaches. Thanks for watching. Okay, so this is the first build of a quarter of the filter. It's essentially fully functional now. It took quite a bit of circuit bending. It was close, but there were a few things that I knew were going to need tweaked. So I've gone through and made the changes physically with lots of low gauge wire, and I've annotated the schematic. So I've got all the changes that need to happen. I think the next hardware I'll go big. I'll just go the full thing, because this has confirmed all the unknown elements to it. So yeah, I'll take this apart and I'm going to go through and just talk through the various bits, because this will serve as a bit of a log, a note to self of what changes were made, what values were tweaked where and why. Yeah, this has got a lot of funky little cables added on. So where to start? If I remember correctly, the first tweaks that I did, there's an obvious one that I'd missed. So this bit here, the left output jack, that was coming from the source pre-limiter, although the switch itself, it was switching the destination to the all-pass filter, so it meant that I was getting a limiter on the right output but not the left output, which was silly. So that's here, and that was rerouted quite simply on the top board here. So I've actually changed this in the circuit itself. So this used to connect to that pin. It's visible on this bit here. So down at the bottom. There we go. So that is that's the 1K resistor here, going straight from the tip, and that's coming from the center, whereas before it used to be from that side, I think. Yeah, pin 3 of that toggle switch. So that's resolved, which is good. It meant that the limiter is actually functioning. Limiter values themselves, still a bit of a work in progress, but I knew I needed to play with the gain values on this, so this was quite straightforward to just trial and error, try out some different values. So that's down here. Yeah, one of the values, 173 I knew would need change, so there are certain passives in the silkscreen ledger that I've highlighted as needing tweaked. Where next? What are R43 and R41? So I don't think I've changed anything there, so I don't know what those are. That could be optional, and this is a changed value. So that's the reference voltage controlling the resonance amount. It seems to be behaving, so it's 43K versus 42K. Seems quite an arbitrary small change, but it's working. This is a weird one, which this one's actually connected on the 1047, and it seems to be a case of that's sourcing a parallel branch of the volt per octave and coarse fine pitch and FM from the output pre-attenuator, and that's looping in and also controlling the resonance amount. So it means that resonance has got a degree of mapped parameter to filter cutoff. I think looking back at the reference circuits where this one was, I think this came from the Surge VCFQ. Yeah, weird one. Like, that was labeled as a maybe populate, an optional one. So I seem to have populated it, and it works. It does something. Okay, next changes. These were critical changes. So this one was fine-tuned. This is for the oscillator mode. When oscillator switch is engaged, it connects this and drops the impedance of these stages between gain cells. It only needed done on one of them, so I hadn't missed that on my 1047 hacked version. This one stays at 47K, and this is the one that changes. So there I just had to remove a part, so that is our 164, which is down here. Yeah, so this actually got some extra changes made because I'm using that point as a connection point. Yeah, so that kind of already sets us off into this whole mess of stuff. Okay, let's start. Where do we start? What all did I change? There's a lot of weird bits bodged in. Okay, let's start here. So this is an interesting bodge. This is in place of the main coarse and fine pots. So what I realized in the circuit, the way that it works, the attenuverter is crude. It basically has this inversion stage for volt per octave, then reinversion, and then that's what gets scaled and attenuated for volt per octave. what I hadn't thought about was the original circuit version, these connected at this point here, like that. So this is a simulation of it. So if I change this over, change that here, so I'll keep it here. So this was the original behavior, this being coarse, this being fine. And they sum in here at this point. So the output being here, this is, you know, ballpark. The pot's centered, whatever fundamental frequency that leaves it at, which I think is about 250 hertz, something like that. This sits at 100 or minus 115 millivolts, and that ranges from down to almost 300 millivolts towards zero, or like can bridge into the positive. So if I send like positive volt per octave here, applied at this point, that can push it into the positive domain. Doesn't seem to have any issue inverting there, like the circuit still works. Actually, it increases in frequency if it's self-oscillating. So here I had to make some changes because I had to put an op amp in, some in my coarse and fine. This is so that I can engage a link switch so that the leftmost filter would control the one to the right of it if the link switch is engaged. So it means that the second filter, this would act as a bias, so that would be an offset based on this, but this was actually combine and control both fundamental frequencies, which will be cool. But to do that, these have to be bipolar controls that sum into a reference point, and that's what this is doing. So here I've got, I switched this out, so if I change this back, that's 115.7. Oh, sorry, that's, yeah, this is right. So if I go here, that's disconnected. So this is original. This would be my coarse and fine, both set to 12 o'clock position, giving me 50k either end, summing in, that results in 115.7. So that was the reference point, that was a target for a null sort of 12 o'clock positioned pot state. So that needs to be a static, so that's what this is here. So this is taking 12 volts and voltage dividing it as if it's a 50-50 pot, and then combining to get the approximation of whatever 82k and 3M3 is in parallel. So that ended up being 78.4. Don't know what I actually used there. No, I think that's correct. I think I had 39.2 or something like that. I had two values that I could put together to get that ballpark result. So that defines, if I change this over here, that defines this center point, and it's pretty close, 160 millivolts. And it means that I can then use a bipolar control over coarse and fine here, summing in. I just fine-tuned these values. 22k made sense going in at that point for unity, and then this ratio seems to work. So coarse frequency range goes up to almost 280, so about ballpark of where it was landing. Going down, it actually goes positive, so that, whatever that means, seems to work. Also needs to be inverted pot control, so pin 3 is negative, pin 1 is positive, which I had to do manually. Actually got the pots the wrong way around as well, so first time round I had to circuit bend this, lift both legs and bridge them across, but because I'm changing this to bipolar, this now became, there you go, so that's pin 1, 2, 3. So 3 is now -5, so that connects down here to the -5 reference. Then that's positive, which is actually on the board underneath that first pin. Yeah, so that works. So these are now going together. They are summing at an op amp, so I'm reusing an op amp that existed on the board before. So that's this one here, which is, yeah, so that quadrant there. So this was a bit of a hack job. There we go. So I had to change this into being an inverting summing circuit following this. So 13k feedback. So 13k is in there. end up just lifting the leg and putting an 0402 in between. So that's a bit there. The output resistor is that 22K, should be 223, yep. And then this is our output source, output trace and input trace. So the input trace falls along here and comes from this point here. So this is my source where it jumps through the board from the main pots. So that is here. That goes to that pin, which is that pin, which is there, and then this pin, which is that pin, which is there. So I lifted both these, just put resistors on pointing up. There's that, whatever value, I think it was 33K and 1M5. I think that's what it was. I should label that. Okay, that was that, then was 34K, and is now 33K. I might fine tune that further at some point, being a red dot. Do the same here, and this was 1M3, is now 1M5. Cool. Okay, so that's what's actually on this board here, I think. 3, whatever that means. Yeah. Then that jumps through the board. How does that jump through the board? Oh, that's what it is. Okay, so I'll come back to that. That was a third source coming in. Okay, so that's the sources from the pot, which travels up here to the input, and then the output following this trace coming back goes to there, that point, which is here. Yeah, that side there. So that is basically redirecting the coarse and fine pots, summing them at their own op amp, inverted, and then summing in here with the volt per octave. So that gives me my new pitch control scheme from bipolar pots, and it means that I can switch that source going to the next filter stage, so that I've got common control, and that would sum with the existing coarse and fine pots as a bias. Yeah, cool. I need to decide what I'm doing. Well, I guess volt per octave is just going to sum on its own, or branch from the normal pin, from the tip to the normal of the next one. Okay, so that's all well and good, but I needed to have an extra. When I switch in the oscillator mode and it bridges this helped allow for some stability of amplitude over the frequency range at the low pass output. But the pitch offset changed and the volt per octave tracking changed a bit. So that was kind of the main bodge, was compensating for that fundamental pitch change as well as the volt per octave deviation. So I needed to add a separate calibration trimmer for offset and one for volt per octave. So the one for offset first, that was this guy. I used, this is just exposed ground. So ground on that side, pulled up to there, wherever that is. Oh, that was quite smart. I was quite proud of that. So this is my logic signal coming from the toggle switch, because the filter resonator oscillator switch, it's using just a on toggle switch controlling DG switches. So in the down position, that pulls this high, which closes that, opens that, so closes that. I rerouted that switch as well, so I'll come back to that. But I was just using that high 5 volt signal because that's a static, like it just gets turned on and off. So that becomes a pull up to this Trimpot. That is a third source. So this is a positive, inverted, summed. So that's what this pot does. So as the toggle switch goes high, that's coming from that pin here, which is, yeah, there. So that pin there, and that pulls across, pulls that pin high. That's the taper, which flips through the board, Goes through here, and some's in there at 150k. I think that is. Yeah, 150k. Cool, so that allows me to compensate for the fundamental pitch to match the pitches of the filter cutoff or center frequency and the oscillator fundamental. Cool, what's next? Switch is the main one. Yeah, switch. So this last switch, I've removed it from here because that doesn't need shorted, so I've repurposed that fourth switch of the DG quad switch, and that is switching in and out this extra Trimpot. So this is our calibration ratio going to gain cells for cutoff frequency, and that was previously 100 ohm variable rheostat voltage divider to a 330 ohm, but this, so it's because there's it droops, so when you go to oscillator mode the tracking droops a little bit more, so I had to open this up a bit, and I did that by increasing the resistor on the pull down of this voltage divider by forcing in 100 ohm Trimpot. So it's in by default, but this is closed, so this transistor here is a inversion stage. So that didn't exist in the board before, so that's been added in. I just scratched off some ground pad here, so that's ground. That's my 1 mega ohm to ground, that's my 1k input to the base, and then that is a 5 volt pull up, so that's coming from here. It's a weird one, so that's a hole in the board that I was using to jump wires through to go there. Yeah, so that's the actual Trimpot. So this is the extra volt per octave compensating Trimpot, just acting as a rheostat. So that goes through the board, through that hole. They come out here and they go there and there, which is, where is that? Here. So that's the 330 ohm. So that's extended. So I'm basically punching in this extra resistor on that. So yeah, that makes sense. So this was moved along. So that was where it was. So it's nudged round one side of the Trimpot, the other side of the Trimpot is going here, and then they come along to there, because this added in the switch. So the whole switch is in parallel to this, so that's why there's a parallel branch. So this is the DG switch. What I did, I removed this chip, cut the trace that's under that pin there. So that was now floating. Lifted this leg. See if I can find a better angle. Yeah, that's kind of visible. So yeah, that leg there. That was a resistor leg lifted up. Yeah, so that's control pins on the far end. So that's the control pin. The switch comes here, and that's pulled up at the collector of that transistor. 10k pull up. It's interesting that's on the wrong side. That's just pulled up. I feel like that should be moved. It seems to have been working. I'll make that change anyway, because that was an error. We'll test this again after. Magic smoke, don't breathe this. So lift that, put that on the inside of that 10k. should do it. That's the pull-ups now after the 10k, between 10k and the collector. Yeah, okay, so don't think that'll actually make any difference because it's still, I mean, that was always closed. I'll need to retest that. That's curious. Okay, well this is now correct based on what I was anticipating it should be, which is fine. So that controls this switch, and then that's one end of the switch, that's the other end. I just removed that resistor, which was previously, oh yeah, it was previously the other 5k6. So that's gone. So that's the other side that goes to that other side. That should work. Cool. I think that's all the circuit bends. Oh, I did, there's an extra bodge here that can be ignored. Like that was me removing a trace and then re-adding the trace. So that's on this bit here. Yeah, that's here. I cut that trace so this was floating so I could send a different level or bypass something. Where's that one? The feedback oscillator, yeah, that's fine. Oh, I made some changes to the tan H as well, so that's no longer a voltage divider, even though it's 1 meg. So that's gone, so that's removed. And that's up here, kind of buried by blue wire. See, just in between, that's removed. And I changed the 13Ks to 15Ks just to boost the gain of that tan H a bit. So that's there and there. Yeah, those two are changed. Wherever they are. Yeah, the middle ones, so middle. That guy and that guy. Yeah, everything appears to be working nicely. So next up I'm going to build a second one. I'm not going to go full detail with all the circuit bends, but the only thing that won't really work will be the volt per octave tracking of oscillator mode, but filter modes work very nicely. So this will give me a reference point just to compare and contrast. Yeah, back to time-lapse. Okay, that was a quick start in Mauser here. So this is me searching for the transistor IC that I end up using in the Kher. Yeah, previously I stuck to just a dual package match pair. That's it there on screen. So that's the two package or the two transistor version versus the SOIC quad version. So there's a nice NPN and PNP equivalent, the same form factor. So this is me just adding that to my library in KiCad. Using the same symbols and just duplicating it so it's got multiple symbols per single footprint. Little glimpse of the simulation there where I was just double checking my circuit works because I rearranged the schematic versus the way it's laid out in the original 1047 EagleCAD module layout, which is from quite a few years ago. So I just wanted to get this a bit neater so it was easier to follow the signal flow. So that's gain cell A, gain cell B. So those are the two stages within the multi-mode filter. Then the third gain cell is used for feedback, for resonance. So already we're in the board view. Like this is way more early on than I typically would do. Normally I would have the full schematic captured and then switch to the board layout and then lay it out around the actual hardware interface. I've not even laid out the jacks or pots at this stage on this, but I purposely did it out of order because I knew this was going to be more of a scratch take where I'm just laying out the board to try it out and confirm the actual analog circuitry. Yeah, so I've kind of jumped into the board layout much sooner than normal, and I'm just trying to condensely pack it in as efficiently as possible, just without any real placement in mind, because I knew I was going to have plenty of PCB real estate to place this on, because it ended up being a two-board layout. Yeah, it's me just trying to align all the routing so that they're direct paths as much on the top side as possible, which is always a bit of a challenge. So here I'm laying out the pitch control circuitry, I think. Yeah, there we go. So you can see those two resistors that are in series together. They're the temperature compensating resistors. So that was kind of another reason to go with a quad package version of the transistors. Added temperature compensation to this version of the circuit versus the 1047. I'm not sure how much difference it made, but I went for as close proximity between the two temp code resistors, or PTC resistors, positive temperature coefficient, yeah. Getting them as close as possible to the transistor packages. So that was the two SOIC packages of NPNs and PNPs with the temperature compensating resistors right in the middle. The odd one out being the VCA controlled for the resonance path, which was an additional pair of matched pairs of dual package transistors. I think the next bits are the resonance control, so that's fleshing out the circuitry around the feedback path. I think at this stage I also add in the strike input section, which is an AC coupled buffer, which basically creates a trigger that goes directly into it kind of like sums into the network. Yeah, that's linking to gain cells. Yeah, that little cluster in the top left, I believe that's the strike input. So it's an AC coupling stage. There's a cap on the input to the op amp. Yeah, so I'm kind of just adding bits of the circuit because this is a schematic that I'm familiar with. I've designed this before. This is just with more stuff added in. So I'm kind of rebuilding it from my existing reference as I go, and trying to keep it logical so that I can get to the stage of routing the traces as soon as possible. So here you see I'm trying to keep it as red as possible, so everything's top layer copper. Yeah, I've tried to place it as ergonomically as possible. The tricky part is picking the particular transistors for the case of the SOIC packages, so that's where which transistor is going where to try and get all the connections as efficient as possible. That and op amps are the trickier part, because a quad op amp is for the same things rotationally symmetrical, but a lot of the times I'm trying to place it so that particular channels have a direct path, and it's not always immediately obvious, so it's always a bit of trial and error as we go. Yeah, so this is fully fleshing out the complete feedback circuit of the filter itself. You can see I'm jumping to Mauser quite regularly as well. I think for that I was just checking whether I had an optimal 0402 version of the right capacitor that was necessary. So a lot of it I'm trying to keep it COG type as much as possible. There, that's the pair of matched pair transistors that are the gain cell for the feedback. So that's been added in as I go. So I'm kind of building the circuit out from as densely packed a shape as possible, because you can see there's little clusters and like islands of bits of circuitry. So that bit there where the components went blue, I placed it on the wrong side for what I realized I needed, so that was a trick where I just grabbed all the components, mirrored them, and then re-mirrored each one individually, and that kept the same symmetrical arrangement. That's a lot of the hardware starting to go on. The jacks, switches, buttons, pots. You'll see as well, like my schematic size, the canvas keeps getting bigger and bigger as I need it more, so I'm just going from A4 to A3 to A2. Here we go, we're in Illustrator now, so this is me cutting out a quarter of the full keihir. I kept the only thing I changed there is the gain pot. I changed that to a tall trimmer, just because I didn't want to have to move the coordinate in to try and, I guess if I nailed the hardware layout, then I could try and duplicate it later on. Didn't end up being the case, but yeah, it meant there was as minimal change to the layout and panel design as possible. Some more op amps going in, so this is starting to add in more 2164s. which is going to be for the various crossfaders and mixing circuits. There we go. So that's the VCA chips. Oh, you can actually see I'm going back and referencing the SSI datasheet for the 2064, which is an excellent datasheet. There's a lot of really useful reference circuitry in that. I think I was just double checking what the passive filtering stages need to be on this version of the 2064. And another 2064. So this one's a bit quirky. So this is split up over a couple of uses. I'm using a few of the channels for the all-pass filtering. So that's 2 cascaded all-pass filters there. So that's me again referencing the datasheet because it's got all the filter circuit references in it. And then this is the LFO. So this is using, that's another thing I spotted. The LFO circuit, there's a version of that documented in the datasheet now, which is really cool. Yeah, it's a really handy little circuit if you just need a basic voltage controlled integrator for getting a triangle wave. There. The schematic's definitely growing. This is me adding some DG switches now. So these are the CMOS based IC single pole single throw switches. Just because a lot of this, when I'm changing the switch states, I didn't want it to go to a double pole double throw switch. So yeah, this was just keeping with the same on-off-on or on-on 2-way and 3-way 3-pin switches. But I'm using them with various different transistor logic to invert the states and redirect controlling signals to change parallel switch states. Here we are. So this is me adding Trimpots as densely around the coarse frequency control as possible. This way all the Trimpots are top facing, hidden under the big knob. Yeah, really handy approach. It means that you don't need to keep flipping the module over to access the Trimpots for calibration. I've done these layouts before, essentially, because I've done versions of the all-pass filter, of the Crosfader. So a lot of it is patterns that I'm quite familiar with in terms of tricks for how to as densely pack the circuitry together. Yeah, especially having like the op amps top and bottom of a horizontal SOIC 2164, when a lot of the channels are used in a sort of symmetrical way, or it's parallel versions of the same circuitry. If it's just a couple of linearized VCAs with common control, then I can kind of do it in a very symmetrical way. Even little details of having the op amps in a particular orientation, it means that the positive 12 rails are all on one side of the cluster of ICs, and the minus 12 rails are the same. Kind of preemptive things like that I think over time I've got better at spotting and being like, okay, if I'm going to be routing power on the backside or on an inner layer, then I might want to keep that as a running pair. There we go. So I'm starting to place all the little clusters of circuitry onto their own board now. So this is where I'm kind of catching up myself in terms of the order that this would normally be done. Because normally I would do this stage ahead of time and then build the actual placement of components around that. But I've done it preemptively in clusters and then split it into 2 boards. So I've got one control board that's got all the interface on it and minimal circuitry. It's got the power regulation, the power headers, bypass and stuff. And then there are a bunch of 2x5 header sets that go between the boards to hold them together, which gives me plenty of places for the circuit to jump between the boards. It always ends up more messy than you hope for in this stage, because you think, okay, well, all the circuitry's on the backboard, that's the filter inputs, outputs, and then control inputs. But then there are other little quirks, because the Trimpots for the calibration, they're all on the top board, but you need to be calibrating the stuff on the backboard, so you then need to have parallel jumps going through to actually reach the Trimpots. Yeah, it gets messy, and all these big branched out highways of parallel traces, which gets fun when you realise, oh, I've painted myself to a corner, I've completely cordoned off this whole section that I need to run a bunch more traces to. So this is the sort of challenging Sudoku puzzle as it keeps evolving, and you need to just keep adapting. Yeah, so this is me putting in the header points. So I put in the headers and match the positions between the 2 boards. In the schematic, I'm using schematic symbols that are discrete. So I'm taking pin 1 of the header on the backboard and pin 1 of the header on the front board and aligning them. So that's where it's creating the break in the circuit path. That way I don't have air wires or nets like running between the boards. Yeah, KiCad's very nice for micromanaging that side of it, because yeah, you can highlight a particular pin on a footprint, and that will take you to the exact location, and then that way I know where the circuit path is. Just nudging things around. So this is after I've brought all the bits of the circuit islands over, and I'm just morphing them a little bit just to get to best fit around the headers. I place the headers as well, and I also do a pass before this routing stage where I decide where the efficient paths are for running a trace between the boards, because I want to try and keep the routing as short as possible. Hard to do when it's split like this, but yeah, there are certain things where I'll prioritize. Okay, this is a cluster of routes that need to be made through to the top board, for instance, and I'll try and group them to a cluster of the headers, even if it means those are branching out to much wider destinations on the top board. Top board's got a lot more space to route around, theoretically, although it's got all the hardware, all the pots and jacks, so there are a lot of through-hole pins to navigate on that side. Yeah, this stage of the design is very different from the schematic capture, I find, where like designing the schematic, there's a lot more that has to be thought about and considered in terms of, will the circuit work? Or having to jump between that and a simulator and trying to problem solve in a certain way, whereas once that's locked in, it's a case of I just need to make all the connections until there are no missing connections. Yeah, this is a stage that you can binge watch shows in the background, and it's a little less active in terms of a thought process. It's a bit more paint by numbers. Here we are. I'm onto the top layer board now, which has fairly minimal circuitry. It's got a lot of passives on it, as well as the power diodes and stuff. So this is more just a case of try and make all the traces as neat as possible, and if I can get them top layer, that's nice, but a lot of them are coming through via points, essentially, or through through-hole points, which means it's easy to just run them either side. But it's quite satisfying getting things as efficient as possible when they're all on one side. There we are, we're onto the faceplate now. So I'm doing this both in the schematic and the board file. For continuity, there's a bit of a trick. It means that if I highlight all the schematic elements that are the pots or jacks or whatever elements they might be, it means if I go over to the board layout, they're all highlighted and selected. That's me matching the coordinates. So this is me adding in all the holes for the Trimpots. So that's just a part that's just a 3.3mm hole, and I'm just like eyeballing it on the board and then just moving all the parts over at once. And here's the process of bringing over the visual aspect, so the graphical aspect. You can convert from an image and it will generate the vector. There's a trick where if you open up in a text editor, you can find all and replace all of like the f.mask or whatever the descriptor is, and change it all to another layer just with a text modification. So that's a trick that I did that I don't think needs done anymore with KiCad 9. But yeah, that's the process.